Hello everyone. Nice to the summer course, the Tankang University 2022. My name is Longjae Yang from Department of Mechanical Engineering, the Tankang University. Today, I would like to deliver an interesting topic about the semiconductor and MEMS. What is MEMS? MEMS. MEMS is the short word, the microelectromechanical systems. I will explain detail about what is MEMS and what is the impact on our daily life about this issue. As the rapid progress, the modern civilization, the human being are stepping toward a challenging time reached of new materials, new technology, and new products. MEMS, the microelectromechanical systems, with merits of small size, multifunction, and a low cost, was regarded as one of the most important techniques for changing human living style. MEMS not only related with many disciplines like material science, mechanics, microelectronics, optics, medicine, biology, environment, and energy, but it's also induced huge impact on our daily life and economical activities. The first scientist who addressed the concept of MEMS, or small technology, is Professor Richard Feynman, the Caltech, California Institute of Technology in US. He is also the Nobel Prize winner of physics in 1965. In his very famous talk, titled as "There's Imprinted Rooms at the Bottom," which delivered in the annual meeting, the American Physical Society in 1959, he revealed the visionary point of view about making things small, very, very small. At the end of his talk, he provided two prizes for anyone, two prizes for call for solution. If anyone can make this, they can get the prize. One is if you can miniaturize any page, any page of a book, but with the size, smaller size, about 25,000 times smaller, then he can give you the prize. 25,000 is very, very small. Actually, you try to make the page of whatever your image or text into an area even smaller than a pin head. So it's a matter about miniaturization, about the information. And second prize, he will give to anyone who could fabricate an electrical motor. Electrical motor is very important to our industry every day. If you can make an electrical motor with a size about 400 micrometer in diameter, maybe you have no idea how large about the 400 micron in diameter. For example, our hair, our hair diameter is roughly about 100 micron. So 400 micron means only 4 times your hair diameter. So it's pretty small. So we can make this micromotor, he also give you the price. So even this idea, the small technology, is beyond human beings' imagination at the time. It actually inspired people through interest about the miniaturization, making things small. In 1984, Feynman delivered another talk with a similar topic, but the title changed somewhat. Title changed to infinitesimal machinery. This lecture was delivered in the JPL, Jet Propulsion Laboratory. Actually, it's the most famous laboratory or research center. They made satellite or spacecraft for NASA. So Feynman revealed his previous talk about there's plenty in the room at the bottom, and proposed some idea, including quantum computers and sacrificial layer method for micromotors. At that time, micromotor not yet realized. So he proposed a method, sacrificial layer method. So in 1989, actually it's 88, the first micromotor in the world was officially announced, like this picture. The inventors are Professor Mueller and his 2 Taiwanese PhD students, Dr. Fan and Dr. Tai. Dr. Fan, later on, he went to IBM Research Center, and Dr. Tai, he joined the faculty board to Caltech. This micromotor has a resolution. His diameter fit the requirement about Feynman's talk. He called for solution, correct? And in his second call for solution, he say anyone can make a micromotor smaller than 400 micron, and you can get the price. Actually, Mueller, Fan, and Tai, they made this micromotor with a size with only a diameter about 100 micron, only quarter about the dimension Feynman asked, request. So it means that their machining resolution right now is not a conventional technology. For the conventional mechanical technology, the machining resolution is roughly about, it should be better than 10 micron. But if you want to make a micromotor like this, the resolution should be down to 1 micron or even 0.1 micron or 100 nanometers. So it's pretty small, And this resolution is similar to the resolution about the IC fabrication. What is IC? Integrated circuit. Right now we enjoy the IC every day. Even you have no idea what is IC. Doesn't matter. In your mobile phone, thousands of transistor IC serve for you every day. Even when you enjoy, right, using your mobile phone. Okay, so the MEMS, the micromotor here, they adopt the technology. We call the MEMS technology. Actually have the similar machining resolution as IC, integrated circuit. But they don't want to do the transistor. They made the sensors and the actuators. Sensor try to detect some signal from our environment. Actuator For example, micromotor is an actuator. But right now the size pretty small. Micromotor. Okay, so we can say this view.
这是全世界最小的人造马达，头发厚度差不多。
So you can see this is the air. It's a hair, human hair. This is a human hair. You can do the size comparison. So comparable to the human hair. So we can rotate with the speed about 300 to 500 RPM. Pretty fast, pretty small. So people today not only can have the semiconductor integrated circuit IC, but actually we can also use MEMS technology, micromotor technology. We try to play around in the domain about the proper for cells, virus, and the DNA. The cells, DNA, they are pretty small, right? But they are moving. They're living and moving. So we have the possibility to play with this biomolecule or biocells in the world about the MEMS. And with a comparable size, the IC and the MEMS devices here, both kind of device, we can integrate both of them together on the same silicon wafer. Okay, we will explain more detail in the following. Okay, in this page, we pointed out 3 merits, the MEMS, 3 advantages. It means the reason why we want to make things smaller, right? Actually, Feynman had ever pointed out. But I summarize here again. Number 1, larger strain. Larger strain. If we make things smaller, the strain is large. It means that if we miniaturize our structure according to the same reduction ratio from any direction in the 3-dimensional manner, we will see this small structure can bear more times, many times, its own weight without being crushed or being damaged. In other words, the small things could have the more slender configuration, like ants, small ants, right? Very slender, very slender leg, slender body, and so on. But they can still perform, running, walking very well, very fast, very elegant, very, agile. But on the other hand, if we look at the big elephant, elephant is on the contrary, very big, size very big, but his motion very slow. And his leg, wow, very giant, like a trunk, right? Very big, not very, right? Very clever, not good enough. So making things small have the large strengths benefit. Number 1. Number 2, better performance. Okay, the better performance may be not very specific, but we talk about natural frequency. Natural frequency, you mean I was checking, right? Natural frequency. I have the size about 1.7 meters, and I have the rest, my natural frequency property about 2 to 3 hertz. For example, I was checking natural frequency. When the size is more, the natural frequency will increase, not decrease, increase. You mean that the natural frequency when it increase, what performance he can have. This object can sense many signals with a frequency feature smaller than its natural frequency. So if your natural frequency very wide, very big, very high, then you can detect many kinds of signal, including voice, acoustic noise. So for example, ants or insects, they can detect and they can hear our voice, even our vibration. Any moment they can sense, because we are low frequency. We are low frequency animal. They are high frequency animal. They can detect. But on the contrary, we cannot hear any voice come from ants or insect. Even whether they can talk or not, I don't know. But we cannot sense. But they can sense from us. So their performance about the sensing is much better than us. So if we can make things smaller, we can also enjoy this benefit. It's the second merit. And the third merit is about the cost, manufacture cost. Very low manufacture cost. Regarding the manufacture process about the MEMS, we'll talk about that later on. They adopt the process about the batch process, B-A-T-C-H, batch. Batch process means that they collect 25 pieces or 50 pieces of wafer working together. That is one of the silicon wafer we have ever developed and the process. So this is batch process. And each of the wafer, you can see hundreds or even thousands those small devices were fabricated on the substrate together with identical dimension, identical function together. So even the fabrication facility or equipment are very expensive. IC factory is very expensive. Similar, MEMS factory also very similar, very expensive. So even the facility very expensive. But because they can generate and produce millions or even billions of devices per year. So when we do the average, each small piece costs nothing. So we can lower the cost. We can lower the cost very hugely. So basically, we have three merits for MEMS: large strength, better performance, and low cost. This is one of the silicon wafer we have ever made in our university. We have ever tried to develop the MEMS pressure sensor. So in this 4-inch wafer, just probably like this size, we made probably about 800 or even 1,000 identical pressure sensor on the same silicon wafer. And we'll talk about the pressure sensor later on for his function. Okay, in this view graph, I want to talk about the fundamental steps about the semiconductor process or even the MEMS process. As we mentioned before, the major MEMS technology was originated from semiconductor IC processing. So we call this kind of MEMS technology is silicon-based micromachining. Silicon-based micromachining. No matter how it divided as bulk micromachining, surface micromachining, or even the CMOS MEMS technology, all of them, they are silicon-based micromachining. So we show the fundamental 3 steps over here. So for each layers, the structure, even for the MEMS structure, whatever sensor or actuator or even the transistor, they are similar. they divided many, many layers, like the 3D printing manner, but we have many, many layers. Each layer, we need these 3 steps: thin film growth, photolithography, and etching. Okay, so you can see the wafer here. In the beginning, is very, very, just blank without anything, only silicon wafer. Then we use the furnace, some kind of furnace, high temperature or low temperature, whatever. They can coat in some specific function thin film on your silicon wafer. Secondly, we cover with a layer of photoresist and doing the process about the photolithography in the yellow room. And there, we use UV exposure, ultraviolet light, or even laser to do the exposure. You can define some part of the photoresist will be removed. So you can protect your silicon selectively. This is photolithography. Actually, this step is very crucial, very, very crucial to IC, even to MEMS. All our design actually settle down on this step. If we cannot do it very properly, we cannot have the correct patterns or geometry on your device. Third step is etching. With the protection about the previous photolithography and the photoresist pattern, then we send the wafer into an etching solution. In the past, we used the wet etching. Right now, we use the plasma dry etching. Plasma dry etching. So we can sculpture or remove selectively about the pattern, or we can pattern the thin film. Actually, we have coating in the first step. So finally, you can have one layer of patterns with this kind of specific thin film on this layer. And really, for the IC or MEMS, we have many different kinds of material. Sometimes polysilicon, sometimes metal, sometimes oxide, nitride, and so on. Many, many different kinds of material. So we need to define layer by layer, layer by layer. But each layer, you need these 3 steps. You need these 3 steps. Okay. Okay, so right now, but as we know, all these fabrication steps or processing are very expensive. Even each price very low, but the overall processing cost very high. So many university and the research center, they cannot afford this kind of money and building cost. So in general, we need to ask help from real IC fab. For example, in Taiwan right now, we have very strong IC industry. And we have very big company like the TSMC, Taiwan's Semiconductor Manufacturer Corporation. It's #1 foundry surface in the world. And another big company is UMC, United Manufacturer Corporation. And UMC, whatever TSMC or UMC, they can be asked to provide service for you, even very costly. But our Taiwan government, we set up a center called the CIC, Chip Implementation Center, CIC in Hsinchu. They call for all the proposal from the professor and the student in Taiwan. So each time they maybe can collect 100 or 200 design from professor, and they lump sum together as a photo mask together, and they can ask the CIC. Now CIC can ask the TSMC or UNC to do the real fabrication for us. So in this kind of manner, this kind of the surface can help professor and the student, even in their campus, they have no facility, they still can do the research about the semiconductor or even the MEMS here. For example, my student here, they do the design in campus in my lab, and they can propose their idea and design to CIC. And after 2 months, they can receive the chips from TSMC. Amazing, right? Very, very amazing. Wow. So even our student from Tankang University, even we have no very, very nice processing equipment, but we can still try to design our case. If we have the good, smart idea, we can still practice the all the facility and the framework about the semiconductors IC and the sensor actuator MEMS area, in MEMS area. Okay, in the following, I want to start to talk about the current products about the MEMS. Actually, MEMS product actually fill our daily life every day, but we have no sense. We have no idea, right? It's something like there's a slogan about a computer. You say the Intel inside, right? Intel, right? Intel they fabricate the microprocessor CPU for all the computer all over the world. So there's a slogan, right? Intel inside. Today actually MEMS inside. MEMS inside our daily life, but we have no sense. So here I want to point out several famous products we use every day. Number one is inkjet printer. Number two, pressure sensor. Number three, airbag astrometer. Number four, projector. Number five, IR imager. UAV, a manned air vehicle. Okay, I will mention briefly about what are they, why they have relation with MEMS. Inkjet printer, all this product, they are billion US dollar business every year. It means that every year, the related product about this kind of domain, they can have the income to the company about 1 billion US dollar. 1 billion US dollar is amazing to our individual person, right? Okay, so inkjet printer, we know the inkjet printer we use every day, right? It changed our OA style, our office. Our office working style changed. When I was a child, my father working in the office, no facility to print out anything. So whatever you want to do the copy, even copy is very, very expensive. The Xerox copy is very, very expensive. Not to say about the colorful printing, right? But right now, everyone can own a colorful inkjet printer. You can print out anything at any time. And low cost, because the printer is a printer cartridge. I believe all of you had ever replaced the cartridge about the printer. Right? And the printer, you can see there are some metal parts. This metal part actually is made by MEMS. Inside, this is the inkjet printing head. The printing head has some small orifice holes and connected with some ink reservoir. And when they can actuate the ink according to their requirement and to print out 3 times the ink. 3 times the ink. Try to mix to a colorful picture on the paper. So it's the inkjet printer. The business is very huge because everyone, when you print out 200 pages of the A4 paper, you need to change the cartridge. So inkjet printer is one of the MEMS product very famous. Second one is the center one is the pressure sensor. Pressure is a pressure sensor gauge, pressure sensor gauge. In the past, the pressure sensor is only used in industrial piping, right? In some industry factory, there's some piping. We need to monitor the pressure inside the pipe. But right now, the application widened to automobile industry. In the automobile industry, right now, all the new car, they are regulated to install the wireless pressure sensor, inside the tires. So all the tires should have some sensor inside. So the pressure sensor inside the tire can transmit the signal about the pressure to our control panel, so the driver know what's up about your 4 tires. If the pressure not enough or even broken, some release, some leakage, you can try to go to fixing right away. So the tire pressure gauge right now very popular, and all of the pressure sensor are MEMS, made by MEMS, because of very, very low price. But even not only confined in the low price pressure sensor, even for the high price, high end pressure sensor, originally in the industrial piping, people still try to replace all of them into the MEMS style, MEMS pressure sensor. Okay, and the third one is airbag accelerometer. Most people know, but not in our automobile. New automobile, we have several airbags. The driver, in front of the driver, or the front seat passenger, or even the backside passenger. They also have some airbag to protect during their impact or colliding with other, accident. Because if it has an accident, the airbag will protect you. Who sends the signal to airbag and then it trigger to explode it? Accelerometer. And accelerometer very similar to pressure sensor, and also a kind of very famous MEMS product, accelerometer. Because right now in one car, right now maybe we have 3 to 4 airbag system. So in each airbag system, maybe you need 2 accelerometers. So you can see many accelerometers are required. All of them are MEMS fabrication. And this kind of product actually is come from the regulation, traffic law. Traffic law come from the United States. They originally they send the order to all the company of the automobile. You need to install the safe system, passenger safe system about the airbag. So gradually emerged a new market about the MEMS accelerometer. And in the next is the DLP projector. DLP is a short word about the digital light process. Digital light process projector. This projector was invented by TI, Texas Instrument Corporation. Texas Instrument Corporation actually is, they have the patent about the integrated circuit, in 1960. So they are the first generation semiconductor company. And about 30 years ago, they started to study the project about the projector. 30 years ago, when people want to do the presentation, we don't have the PowerPoint. PowerPoint is just the idea 20 years ago. So how do we do the presentation? We use transparency, and we use some pen to write in something on the transparency and use the hand-up projector. Not this projector. So when TI, they have the good sense about using MEMS technology to develop the new generation about projector. From that time on, changed our presentation behavior all over the world. So right now, even me, at this moment, I use PowerPoint to do the presentation, right? If I in the classroom without the DLP projector, I don't know how to deliver my knowledge to you. maybe I need to write something on the blackboard, right? Very stupid way. So DLP right now, they spend a lot of time about developing this kind of MEMS product, and so they produce a very big impact to change our living style. And next one is IR imager. IR is what? Infrared. Infrared is a kind of thermal signal from our hot temperature body, for example. So you can see this picture, right? It is an ordinary, picture in our visible, our visible light, right? And the right one is IR imager. It's very often be found in some hospital or in the airport, right? Right now, airport and hospital or in any public place, they adopt IR imager to detect the passenger, try to find out who is possible infected by virus. We don't need to take temperature from everyone. It's time consuming. So we just scan, and you can see we have some image, IR image over there. They can show whether your body temperature is too high or not high. And the IR imager actually is a kind of MEMS product. Without the MEMS technology, we cannot enjoy very convenient IR imager and very low cost IR imager. IR imager actually, his first application is about the military surveillance, military use. For the nighttime, for the soldier, if they want to see the enemy in the nighttime, they need a telescope. The telescope embedded with IR imager, so they can see any enemy at night, and they can shoot. them. So IR imager come from, actually their first application is in military use, but gradually they switched to the commercial use, to hospital, airport, non-contact body temperature detection. Very important, especially during our COVID-19 pandemic period, right? The last one is UAV. UAV. What is UAV? A manned air vehicle. It means a manned aircraft. No people, right on the aircraft. So this aircraft is very small, a small size. In this aircraft, many sensor and actuator. Actually, they are MEMS as sensor and actuator embedded inside. Many sensor, even motor, battery, many things. Pressure sensor, accelerometers, gyro, many things that can integrate together. So UAV right now very popular in our whatever military surveillance or even entertainment, right? Festival entertainment. In many occasions we can find the UAV. So you can see I just only show 6 types of example about the MEMS. And all this stuff, all this product, we know that, witness that, we know their impact. Yeah. Without MEMS, all this previous application almost impossible. And regarding UAV, in the next hour it is my another topic I want to talk about in the next step. Okay, finally I want to give a conclusion about the MEMS technology. Compared to the semiconductor IC, we know very important to us, everyone. And what maybe you will think about what is the revenue, annual revenue. Annual revenue about the semiconductor IC, probably about $600 billion US. 600 billion, not million, billion. Billion. $600 billion US every year. And how about MEMS? How about MEMS? Maybe you will ask this issue, right? How about the money you generate? Even they are using almost a similar fabrication process, but the target different, right? How about the MEMS? I can tell you, MEMS revenue very less, only 20 billion US dollar. Only 3%. Only 3% about the semiconductor IC. So it's a very, very minor. If you only compare about the revenue, yes, it's a very minor. But if you look at their function or production, right, or products we just mentioned about, you will feel it's still fine, right? Its application is important, but the real revenue not very big. So as mentioned here, revenue about the MEMS is not big enough. Not big enough. It's true. It's true. So regarding this one, the main reason may be that semiconductor industry, they are focused on making the only one product. I see only the product about transistor. Even IC, integrated circuit, just collect mediums, the transistor together at the circuit. So they have some function. So you can see, semiconductor industry, they only focus on one product, transistor. And they try to make the most of the time and effort to enhance the performance of transistor only. So they can make it very, very nice and collect in the very high density, very amazing function. But how about MEMS? MEMS is not transistor. We made sensors and actuators. Sensor, something like, pressure sensor is a sensor. Accelerometer is sensor. IR imager, sensor. So this three kind of product, they are sensor. And what is the actuator? Inkjet printer. It print out something, right? It's some motion, so it's the actuator. Projector, it changes the light. So they have some motion about the light, right? Image, moving. So it's actuator. UAV, also actuator, very apparently. It can move, it can fly in the sky. It can survey many, many things, right? So the product, the feature is quite different. It doesn't like the single one transistor about the IC. So it's not only the signal processing is only one part of the MEMS. The most important part about the MEMS is very diverse. You need to detect, transfer signal, right, the sensor, and transfer back to motion for control. So it means the MEMS industry, they need the multidiscipline cooperation, multi-domain. For IC fabrication, you maybe only need the help from electrical engineering, right? Or even the material science, physics. They know how to design the transistor, how to develop the new kinds of transistor. Only focus on transistor. But for MEMS, wow, very wide. You need a cooperation from many, many different fields. Otherwise, you cannot do the research about the sensor and the actuators. So it's very, very diverse, very, very difficult to integrate all kinds of know-how from the different fields. So the reason why, right now, even we have several kinds of product, but very limited. Yeah. Even the above the product, they are killer product, right? They can generate billion US dollar revenue every year, but totally still very limited. So one point of view about the future about the MEMS is, okay, maybe we need to explore, we need to develop more killer products, right? Try to generate larger revenue. This is one opinion. But the second opinion is what? MEMS actually not only a killer product idea. MEMS is an add-on technology. Add-on technology. This technology can increase your add value of your original engineering problem. For example, if you are a civil engineer, you build a house, apartment, and if you know MEMS, you can apply a MEMS, product in your building, so your building can become a smart building. The building can sense something, and it can output something, interact with your environment, right? So it's an add-on technology. MEMS is a possible add-on technology to benefit your original engineering problem. So it's the second point of view. Yeah. If we can try to widen the application about the MEMS to all fields in our daily life, I think the impact will getting huge, more apparent, and influence more. This is my point of view. MEMS is a good platform to integrate different expertise into one specific system. Through implementing a MEMS system, people need to learn much by multi-force of communication and crosstalk. You know, I'm doing the research about the MEMS, so I need to cooperate with many professors, not only in our mechanical field. I need to cooperate with EE, electrical engineering, material science, chemical engineering, right? Computer science, and many different people I need to cooperate with, even sports science. Recently we cooperate with some professor sports. So you need to learn much more from this kind of crosstalk and communication. So we are like to quickly accept new kinds of challenge, which may be this kind of challenge. I think with more talk and cross-talking now, we will know more problem, and then we will try to widen our cooperation and try to target and try to solve some important problem. For example, right now in our world, we have many problems, right? Energy problem, carbon emission problem. How do you know this situation is serious? We need sensor, right? And how to change the situation? We need actuator. But our own one people is enough? Not enough. 100 people or 1,000 people, 1 million people enough? Maybe not enough, right? So we need to try to develop our future technology, add with MEMS. MEMS can try to change some situation, right, our current world. This is my idea and my vision. Yeah, limited to the night time, I cannot talk too much. I just give you a concept about the MEMS, small technology. So next time, when you drive your car, maybe you can say, oh, I have MEMS in my car, right? I have MEMS. When you do the presentation to your audience or in your classroom, you can see, projector, I know, it's a MEMS product, right? I hope MEMS will always with you, and you can, maybe in the future, you can also do something beneficial to this new field. Thank you for your attention. Look forward to share my experience with you in the next hour about another topic. Thank you. See you. Bye-bye.